So, when you think about chemistry, what pops into your head? Probably a lab coat, right? Maybe some bubbling beakers, a cool explosion. But the truth is, the real chemistry lab is all around you. It's happening in your kitchen, in the air you breathe, even inside your own body. Today, we're going to pull back that curtain and learn the language of these everyday miracles we call chemical reactions.
I mean, just think about it. That milk that goes sour if you leave it out, that's a chemical reaction. That rusty old pan in the cabinet, another one. Cooking dinner, digesting that dinner, even just breathing in and out. These aren't just things that happen. They're all incredibly complex, perfectly timed chemical reactions. Our world is basically one giant, non-stop chemistry experiment.
So what did all these things have in common? Well, they're all chemical reactions. And that just means it's a process where the actual identity of something changes. You know, you can melt an ice cube into water and then freeze it right back into an ice cube? That's just a physical change. But you can't unburn a log of wood, can you? That's a chemical change. The wood is gone for good, and in its place, you have something totally new.
Now, those everyday examples are awesome. But to really get what's happening on a tiny molecular level, sometimes you need to see a change that's, well, impossible to miss. So let's head into the lab for a classic experiment. Check this out. You take a simple ribbon of magnesium metal and you burn it. It just erupts in this dazzling, super bright white flame. And what's left behind? It's not a shiny metal anymore. It's this completely new thing, a crumbly white powder called magnesium oxide. This is the definition of a chemical change. You can't just cool this powder down and get your ribbon back. It has been fundamentally transformed.
Okay, a dazzling white flame is pretty obvious. But, most chemical reactions are way more subtle than that. So how do we spot them? Turns out there are 4 key clues you can look for.
Think of this as your chemical detective's checklist. Whenever you're watching something, just ask yourself, did it change state, like a liquid suddenly becoming a gas? Did the color change unexpectedly? Are there bubbles of gas appearing out of nowhere? Or, hey, did it get hot or cold all by itself? If you spot any of these telltale signs, chances are you're witnessing a chemical reaction.
So, we can spot reactions. Great. But how do we talk about them? I mean, writing out a whole long sentence for every single reaction would take forever. Science really needed a better way, a kind of universal shorthand.
Let's go back to our magnesium example. Describing it in a full sentence like that is just so clunky, especially if you're in a lab. Chemists all over the world, speaking all different languages, needed one clear, concise way to communicate these things. They literally had to invent a new language.
And here's how that language evolved. You start with that long sentence, right? The first step is to simplify it into what we call a word equation. Already much better. But the real game changer is the final step, replacing the words with chemical symbols. Mg plus O2 yields MgO. All of a sudden, anyone, anywhere on the planet who knows the symbols knows exactly what happened. It's just so elegant and efficient.
Now, this new language has a really simple grammar. Everything on the left side of that arrow, those are your reactants. Just think of them as the ingredients you're putting into the recipe. And everything on the right side, those are the products. That's the final dish you made. The arrow itself always points from what you start with to what you end up with. Simple as that.
But just writing down the symbols is only half the story. There is one more absolutely critical rule that governs every single reaction in the universe. And to follow it, we have to do something I call the Great Balancing Act. And this is the rule right here, the law of conservation of mass. All it says is that you can't create or destroy matter in a chemical reaction. Think of it like playing with Legos. You can take apart a Lego house and use those same bricks to build a car, but you still have the exact same number of bricks you started with. Atoms just get rearranged into new combinations. They don't just pop into existence or disappear.
So let's apply this to an equation for iron reacting with steam. If you look closely, our Legos don't add up. We start with 1 iron atom on the left, but we somehow end up with 3 on the right. And we start with 1 oxygen, but end up with 4. This equation is unbalanced. It's breaking that fundamental law. So our job is to solve this little puzzle and get it to balance.
Okay, let's walk through this together. The key is to just go one element at a time. A good strategy is to start with the most complicated-looking thing, which here is that Fe3O4. Let's focus on the oxygen. We need 4 on the left to match the right, so we'll put a big 4 in front of the H2O. Now, that gives us 4 oxygens, but it also messes up our hydrogens, right? We now have 4 times 2, which is 8 hydrogens on the left. No problem. We just hop over to the right side and put a 4 in front of the H2. Now we have 8 hydrogens on both sides. We're so close. All that's left is the iron. We have 3 on the right, so we just need to put a 3 in front of the Fe on the left, and there we go. Let's do a quick final check.
And look at that. 3 iron on the left, 3 on the right. 8 hydrogen on the left, 8 on the right. 4 oxygen on the left, 4 on the right. It is perfectly balanced. And this is so important because balancing an equation isn't just some math problem. It's about making sure our written description actually matches what happens in the real world, where atoms are never ever lost.
And you know what? We can make these equations even more descriptive. By adding a simple little symbol in parentheses, we can show what physical state each substance is in. You use S for solid, L for liquid, G for gas, and AQ for aqueous, which just means it's dissolved in water. Now our equation tells a much richer and more complete story.
All right, now that we have this amazing language, we can start to see that reactions aren't all just random. They can be grouped into families, almost like genres in music or movies. Let's look at 2 of the most basic types.
So you can think about it like this. A combination reaction is when 2 or more things get together to form one new thing. So A plus B makes AB. A decomposition reaction is the total opposite. It's like a breakup. One complex thing, AB, breaks down into its simpler parts, A and B.
Here's a perfect example of a combination reaction. You take 2 different things, solid calcium oxide, which is called quicklime, and you add it to water. They react together to form just one single product, slake lime. It's that classic getting together reaction. 2 become 1.
And now for the breakup. If you take one reactant, like this solid ferrous sulfate, and you heat it up, it doesn't combine with anything. Instead, it decomposes. It breaks apart into 3 separate, simpler products. One complex thing becomes 3 simpler things. A textbook decomposition.
So there you have it. We've gone from the kitchen to the lab and back, and we've learned the fundamental language of how our world works. You now know how to read and write the story of how matter changes, one molecule at a time. And the coolest part is, this isn't just for a textbook. Now you can look around and see the world like a chemist does. So what hidden reactions are you going to spot today? The world is full of them, just waiting to be noticed.